So for this lesson we're going to be looking at solving trigonometric equations, and to some extent as we go forward with this solving of equations we're going to be looking at it in the context, or at least remembering the context, of trigonometric identities, which are that's the other main topic we've looked at in this unit, and the different identities, development of the different identities leading up to actually proving identities. So be prepared for when you solve a trigonometric equation. Sometimes it's going to be in a form that you can't actually deal with as it's written, and you may have to use various algebraic techniques, one of which is trigonometric identities, but I don't want you to think that that is the only one. And I've even prepared my examples for this lesson to illustrate both the idea of using identities, but also that you not be rushing to judgment when using them. Some things that I want you to keep in mind as we go through this lesson. Just remembering, first of all, we're going to be solving what are known as linear trigonometric equations with this lesson. So what does it mean to solve a linear equation? A linear equation means that the primary component, in this case is just the unknown, is of order 1. In the case of a trigonometric equation, a linear equation means that the trigonometric ratios are all order 1. So for example, there's no sine squared, there's no cosine squared involved. It's just linear. So you might have a sine theta or a cosine of x or something along those lines. Now when we solve this linear equation, how do I do that? The key here is to isolate my unknown. That's really poorly written. So I want to isolate my unknown. So in this case, I would take my 2x to the other side, subtract 2x from both sides, that becomes 2x. I would add 5 to both sides, that becomes 8, and I end up with my answer, or my solution, which is x equals 4. The other thing I want you to remember or keep in mind is related acute angles, and this is whenever we are solving. So whenever we are solving a trig equation, we're going to make use of these two ideas a great deal: related acute angles and the cast rule. And there are other ways to do this, but this two-step approach is going to be the most consistent, most reliable way for you to do that. Now let's talk about this. And I know this looks quite wordy, but the rest of it is just examples. So when we're solving a trigonometric equation, we're looking for angle values that satisfy the given equation. Because of their periodic nature, technically that means we have infinite solutions. So what we will normally do is also, there'll be a restriction. So I really should say here, satisfy the given equation and restriction, because there's almost always going to be some sort of restriction on the values. A typical restriction might be that 0 less than or equal to theta less than or equal to 2 pi, for example. So that's an example of a restriction that you might see for a trigonometric equation. So the first thing, our equation should only involve one trig ratio. If we have more than one ratio, we're going to use identities to modify the equation. But again, a little amendment I'd like to make to this one, which is, I say to use identities, but sometimes we might just use algebra to modify the equation. And you'll see I've got an example in this lesson where I'm going to be talking about that. And the reason why we do that is because we want to do this isolation of a trigonometric ratio. Then we're going to solve for the related acute angle using the same process that we've done. Steps 3 and 4 are going back to the very beginnings of solving trigonometric equations. Solve for the related acute angle, which is the positive value, and then use the actual sign of the ratio that you get from the cast rule. Usually, if you're doing something like this, typically you can expect your answer to have 2 quadrants, but it's going to depend on any horizontal stretches or compressions, and to some extent any horizontal phase shifts. And then once we've got our quadrants, we've got our related acute angle, we can find our answer using the or answers. Usually there'll be more than one answer. Depending on the restriction, meaning depending on the values of theta, you might also have to continue more periods. You might have to actually add multiples of 2 pi to your answer, or add multiples of the period if it's not 2 pi. So let's go ahead, dive into that, and see if we can start with something very simple. We've got solve the cosine of theta is equal to negative root 2 over 2 with a very typical set of values or restriction on theta, 0 less than or equal to theta less than 2 pi. So I see root 2 over 2, and the special triangle that goes along with that is the 1, 1 root 2 triangle that goes with the angle pi by 4 and pi by 4. So the first thing I'm going to do is find my related acute angle. And so the cosine of the related acute angle is the same as the cosine of the angle in question, except for we always get rid of the negative. We only use the positive. So this is going to be the same as root 2 over 2, or you might have written this as 1 over root 2. It just depends on how you've remembered your special triangle. I typically remember it as the 1, 1 root 2 triangle, but some people also would remember this triangle in the following way. So then they would have 2 root 2 root 2 and pi by 4 and pi by 4. It's exactly the same thing. And actually all I've done to go from this one to this one is I multiplied everything by root 2. Root 2 times root 2 is root 4, which just turns into 2. So it just depends on how you've memorized this, how you're comfortable working with it. And so from there, my related acute angle is obviously pi by 4. Now I'm going to use cast. So I take a look, C-A-S-T. I go to my original, which said that cosine was negative. And so I ask myself, where is cosine negative? It's negative in quadrant 2 and in quadrant 3. So in quadrant 2, my value for theta is going to be equal to, quadrant 2 is going to be pi minus the related acute angle, which is equal to pi minus pi over 4, which is the related acute angle we found in the previous step. And that gives me 3 pi by 4. And that's one of my values for theta. And then in quadrant 3, the angle is defined as pi plus the related acute angle. So that is equal to pi plus pi by 4, which is equal to 5 pi by 4 if we just combine those fractions. Just a quick aside, I just want to make sure that's really clear. In quadrant 2, if that's my angle theta, and here's my related acute angle, then the way I can find this angle theta is I can come all the way around here to pi and then go back by the related acute angle. That's how I ended up here with pi minus the related acute angle. If I'm over here in quadrant 3, then the way that I do that is I go all the way over here to pi, and then I add the related acute angle. And so that's what I had here, pi plus the related acute angle. So there we go, we have two answers. And in this case, because there are no horizontal compressions, the period is not changed, so the period of cos theta is 2 pi. So getting my two answers between 0 and 2 pi is sufficient. Those are my options. And you might, for clarity, you might choose to label those theta 1 and theta 2, solution 1 and solution 2. Now here's a more complicated looking one, and it's still linear in the sense that each of the trigonometric ratios is linear, but this is actually a trig ratio times a trig ratio, which is going to complicate things because technically that would be quadratic. So how do we get away from this? And the question here, well, can we use algebra to get away from this? And really there is not a lot of algebra that I can do here. If I were to, for example, let's start with the algebra that seems quite obvious. 6 sine theta cos theta equals, and I'm going to subtract 3 from both sides, so I get that equal to 2. But unfortunately, there's nowhere else I can go with this. You might think, okay, well, if I've got these things multiplied together, if I can get it equal to 0, so you might say, okay, well, 6 sine theta cos theta minus 2 equals 0. And now what? I can divide everything by 2, but that still doesn't really take me in a particularly useful direction. So instead, what I'm going to do is point you towards the idea of using identities. I'm going to remind you of one of the identities that we've developed in this unit, which is that sine 2 theta is equal to 2 sine theta cos theta. And if I look at this, 6 sine theta cos theta, well, what I really have here then is I have 3 times 2 sine theta cos theta. And that's just knowing that 6 is equal to 2 times 3. Now, if it didn't work out nicely that way, the other thing you could have done is rearrange this for sine theta cos theta and just replace. So that would have been divide both sides by 2. So where I see 2 sine theta cos theta, I can replace that. So now that's 3 sine 2 theta equals 2. I'm going to divide both sides by 3, so I end up with sine 2 theta equals 2/3. Pause for a moment here. Now we're once again going to apply the same next steps, but I'm going to recommend, until you're really comfortable with this, I actually recommend that the next thing you do is a substitution. So I'm going to say let sine of x equal 2/3. So what 2/3, sorry. So what I'm essentially doing is I'm saying let x be equal to 2 theta. I'm taking away this potentially confusing part to start with, and I'm just going to solve this equation first. So I've done that extra step. And so once again, though, I'm going to start with the related acute angle. And in this case, since sine x equals 2/3, then my related acute angle is going to be equal to the inverse sine of, now this one's already positive, but I would make it positive no matter what. And so from there, I get the inverse sine of 2/3 is equal to 4 decimal places, which is kind of traditional for trig. You can keep more, or even better is you can write 4 decimal places here, but keep all of them in your calculator if your calculator skills are up to the task. So now I've got my related acute angle. Step 2 is I'm going to apply my cast rule. And we can see from this, sine was positive. So where's sine positive? That's in quadrant 1 or quadrant 2. So my quadrant 1 answer is going to be that x equals, and it's what we already had, 0.7297. And in quadrant 2, x is going to be equal to pi minus 0.7297. And that works out to be equal to pi minus my previous answer is approximately 2.4119. And that is for this equation, sine x equals 2/3. But that's actually not what I have here. What do I have here? I have 2 theta. So now each one of those, I'm going to go back and now say 2 theta is approximately equal to 0.7297. 7297. And so theta is approximately equal to, and I'm going to divide this by 2. So 0.7297 divided by 2. Now, I'm not keeping all of those decimal places, so I'm actually running into a problem here, which is my rounding is going to get successively worse and worse here. So it would be better for me every time that I do this, even if I have to, I could go back to this calculation and I could put that into my calculator, sine inverse of 2/3, and then I'm going to divide that by 2, and I end up now with a much better answer of 0.3649. And I'm going to do the same thing with this result, which is 2 theta is approximately equal to 2.4119. So theta is approximately equal to, and so once again, I've gone back to my original calculation, so it's pi minus that answer, and I divide that by 2, and I end up with approximately 1.2059. And the other thing I need to keep in mind, or at least make a note of, which is my original equation, sine 2 theta. So there's actually two ways to deal with this next part. We had our original equation, which is that sine 2 theta. What kind of transformation is this? This is a horizontal compression by 2. And so that means my period is equal to 2 pi divided by 2, which is just equal to pi. So on the interval that's specified, 0 less than or equal to theta less than 2 pi, I can actually fit another full set of values. So I could add pi to this one, and I could add pi to this one. And so now I have a theta 1, a theta 2, theta 3 is going to be equal to 0.3649 plus pi, which is approximately equal to 3.506. And I'm not going to, that next decimal, I'm not sure about it because I used the rounded value there. And then theta 4 is equal to 1.2059 plus pi, and that's equal to approximately 4.347. So you can see I have 4 answers here: theta 1, theta 2, theta 3, theta 4, because of that compression. Another way to think about that is to go all the way back up here and look at this condition, which is 0 less than or equal to theta less than or equal to 2 pi. So let's go ahead, let's go down here and look at this another way. 0 less than or equal to theta less than 2 pi. But when we did our original equation, we had 2 theta. So what I'm going to do is multiply everything by 2. So this 0 times 2 is still 0. Then I get 2 theta here, and 2 times 2 pi is 4 pi. So however you prefer to look at it, if you want to look at this as a compression, then that means the period of the transformed function is only pi, which means I need to fit an extra period in, which means I add 1 period to each of those. Or you can look at the interval that we're considering, and you can modify that interval to match the equation, because the equation was written in terms of, I wrote pi here, I should have written theta. Because the equation was written in terms of theta, in terms of 2 theta, then you can see here from 0 to 4 pi is going to be my interval for 2 theta, which again tells me I'm going to have to fit in an extra period. Now the way I would do it then is I would start here with this 2 theta, and I would add 2 pi to that one. and I would take this value of 2 theta and I would add 2 pi to that one, and then to solve for theta I would still divide by 2. I think that for where you should be right now, I think this way should make the most sense logically. I think most people should be pretty comfortable with transformations at this point. But I know that this is a way that has also been taught by me and by other teachers. But either is valid. The hard part is deciding, am I going to add pi to my final answer, or am I going to add 2 pi when I'm only partway through my algebra and then let the division take care of itself? Okay, and that's it for this lesson. As you can see, even with a fairly simple looking question on the previous example, things can get fairly complex, and as we move on to the next topic, which is quadratic trigonometric equations, it can go even further.